All right, first we start with our definitions. Given a graph G, a matching is going to be a subset of independent edges of G. So in particular, that means you've got a subset of edges with no two edges intersecting in a common vertex. The size of the matching is going to be the number of edges in the matching. So given a matching, a vertex V is considered saturated if it is incident to one edge. So if there's a vertex that's not on any of the edges, that one would be unsaturated. For instance, if I had another vertex out here. All right. A set is saturated if every vertex in the set is saturated. And that's just there to allow us to refer to other definitions later. And so there's certain types of matchings we're going to be interested in. The first type of matching is called maximal. That means that you cannot add any more edges to the set and still have a matching. So in other words, for any edge outside the matching, it has to be incident to an edge that's in the matching. Otherwise, we're going to be interested in the maximum matching, which is the matching of largest size. Note here, I should say a maximum matching, because we can't guarantee that a maximum matching is unique. We're going to say that a matching is X matching if a subset X is saturated. So a matching is X matching if every vertex in X is incident to an edge. Finally, if your matching is V matching, we're going to call it perfect. So a graph with a perfect matching, every vertex lies on at least one edge of the matching. So some real-world applications for matchings. The vertices could be people, and edges can represent compatibility of some kind, and then your matching would be splitting the group up into pairs so that everyone is with someone they are compatible with. So for our first major part of the study of matchings, we're going to focus on bipartite graphs. Mainly, one reason is because some of the theorems are unique to bipartite graphs, but the other reason is because of real-world applications. For instance, if you're trying to match job applicants with positions or something like that, you clearly have a bipartite structure. One part of the bipartition are the applicants, the other part are the job positions. And so that would be the real-world application right here. You draw edges if person A applied to job B, and then what you're looking for is this condition. On the side of the employers, A would be the set of jobs, so you want to guarantee that every position gets filled. And so what's the theorem? If you've got a bipartite graph with bipartition A and B, then there's a matching which saturates every vertex in A if and only if this condition is satisfied, which we refer to as Hall's condition or Hall's marriage condition. The condition is that for every subset of A, the size of the neighborhood of S is at least the size of S. So in other words, for any S, the size of the neighborhood has to be larger, at least as big. And so this is an if and only if theorem, so we have to prove both directions. First, we show that if a graph has an A matching, then Hall's condition has to be satisfied. So suppose we've got our A matching. For each element in A, there's a unique element in B, which we're going to call M of A, with the property that A and M of A are incident together in the matching. In other words, if you already have a matching, each vertex in A is on an edge in the matching, and that edge can only have one endpoint in A, so its other endpoint has to be in B. All right, so let's take a subset of vertices in A. Then we notice that the subset of the alternate endpoints on the matched edges, M of A, is a subset of the neighborhood of S. And because of this uniqueness property, the size of these matched vertices is equal to the size of the original set. And thus, the number of neighbors is at least the size of the original subset. The other way to see why this result would be true is to just take the contrapositive, and the contrapositive would be saying that there exists an S such that the size of the neighborhood is too small. And so the way to think about that is, for instance, if we're thinking about S as the set of job applicants, you're saying that if you look at this subset of the jobs, the total number of applicants who had applied to those jobs, some subset of those jobs, is less than the number of positions. So logically, it follows that even if you were to assign people at random, you'd have to have a job left over that's unfilled. So now we need to prove the other direction. In other words, we're going to assume that Hall's marriage condition is satisfied, and we have to prove that a matching exists. So we're going to do this proof by induction on the size of A. So G is going to be an AB bipartite graph. And in the first case, let's assume that a stronger version of Hall's marriage condition holds. In other words, that the size of each of the neighborhoods is strictly larger than S for every subset in A. Then what we're going to do is we're just going to take an arbitrary vertex in A and match it, and then remove it from the graph. So take a vertex in A and take one of its neighbors. We're going to match these two together, so let's delete them from the rest of the graph. And what we want to show is that Hall's marriage condition holds for G prime. So this gives you a recursive algorithm that you're matching one edge, and then you apply recursion to create the rest of the matching. So we need to take our new set A prime is A take away V. Notice that it is strictly smaller than A. So if we can prove Hall's marriage theorem condition holds for A prime with respect to G prime, then we know G prime has a matching. So let's take a subset S in this A prime, and let's look at the number of neighbors of S in G prime. Well, given a vertex in S, any neighbor of that vertex in G prime was already a neighbor in G. But we do run into one little issue, which is that the vertex W might have appeared in the neighborhood originally. So either we're going to get equality between the size of these two sets, or the original neighborhood might have been one bigger, which means that the neighborhood of S in G prime is at least as big as the neighborhood of S in G minus 1. So just ignore W. But because of this condition, we know this set inequality is strictly bigger than the size of S minus 1. And thus, we know that the size of the neighborhood of S in G prime is at least the size of S, which is the conclusion we wanted down here. And thus we have shown that Hall's marriage theorem, or Hall's marriage condition, is satisfied for G prime, so we can apply induction. So this is the pictorial drawing of this case. You can check that the neighborhoods are all strictly bigger. The idea is you remove one vertex, edge, and now we're applying induction to this new graph. And this shows that the condition is satisfied, so we can apply induction. So then, by induction, G prime has a matching M prime, which saturates A take away V. So in our smaller graph, we found a matching by induction. Then the idea is we just add our new edge back, our edge VW back in, and show that we still have a matching. So you add that edge back in, we get a matching which saturates A. The reason why we know this must be true is because we had removed V and W from G to get G prime. So we know none of these edges in M prime could be incident with V or W, because that would imply V and W were in G prime. So this is, in fact, a matching. Otherwise, we have to be in case 2. This would be the other situation you could have, which is that Hall's marriage condition holds with equality for some subset A prime. That's not all of A. The strategy here is going to be to take your bipartite graph. You got A prime, you got the rest of A. And basically the idea is to split the graph into two parts, two bipartite graphs, and then apply induction to each of them to find a matching inside each. And that's what we're going to do. We're going to let G prime be the graph on the left, which consists of A prime and the neighbors of A prime. And then G double prime is going to be the rest of the graph. So for any S in A prime, the neighborhood of S in G prime is the neighborhood in the original graph. And so because we already know Hall's marriage condition holds for the original graph, we know that we have to have this inequality. Thus, we see that Hall's marriage condition holds for the graph on the left. Because A prime is a proper subset of A, we know this graph has fewer vertices, so we can apply induction to create a matching in the graph on the left. We know it exists, which saturates every vertex in A prime. So then we have to check that Hall's marriage theorem holds for the condition holds for the graph on the right. And then by induction, we can create a matching here. And since we see that there's no edges going across, we can guarantee that the union of these two matchings is also matching. So let's take an S over here. And then what we want to do is compute the size of the neighborhood of S with respect to G double prime. And so that's going to take some thought. What we do first is we actually add all the vertices of A prime to S and look at the size of the neighborhood in the original graph. Because we satisfy Hall's marriage condition, we know this neighborhood is at most the size of S union A prime. Since A prime and S have no vertices in common, this set has size the sum of the size of S and the size of A prime. So our strategy is to prove a similar equality regarding the neighborhoods. And the reason why we want to do that is because we already know the size of the neighborhood of A prime and G is equal to the size of A prime, so we'll be able to cancel and get the condition we wanted. So let's prove that. Let's look at the neighborhood in G of S. There are two possible types of edges in the original graph. There are the kind we want that stay on the right, and then there's the kind we don't want, which happen to cross over. And so you can separate this neighborhood into two parts. It's the neighborhood of S and G double prime, the blue edges, union the things that end up over here. And in this case, anything that ends up over here, because this is the neighborhood of A prime, has to be incident to an edge from A prime. So it's just the neighborhood of A prime and G. The thing we note is that based on how we defined our graphs, these two subsets are disjoint, so the size of the union is the sum of the individual sets. So this is just summarizing what we have so far. And so our point is that we've managed to calculate the size of this neighborhood of S union A prime two different ways. One with a lower bound, that it's at most the size of S plus the size of A prime. But we've also shown it's actually equal to the sum of the sizes of these two neighborhoods. And the main point is that this term on the right-hand side of these two sums is actually the same number by choice of A prime. And so thus we can actually cancel this number out from both sides. And thus we get that the size of the neighborhood of G double prime and S plus the size of A prime is equal to, so this is just putting these inequalities together. And the point is we can cancel these two. And what do we see? We see that the size of the neighborhood of S and G double prime is at most the size of S, at least the size of S. In other words, Hall's marriage theorem holds for the graph on the right, which means that by the induction hypothesis, we can create a matching M double prime. And now, as said before, you glue the two matchings together and you get a matching of G, which saturates A. And that concludes the proof. And you can see the proof gives a recursive procedure for constructing the matching. In terms of computational complexity, I will admit that this procedure is quite inefficient because you're looking over a whole bunch of subsets just to see if one of them has the same size as its neighborhood. And in practice, that takes exponential time. So those who are interested can look up There are faster algorithms for finding the maximum matching in a bipartite graph. However, we stick with this proof for this course because it's one of the simpler proofs to give and because you clearly see where Hall's marriage condition gets used. As a corollary, I will point out that using Hall's marriage theorem, you can prove that every k-regular bipartite graph must have a perfect matching.